Okay, let me illustrate some of the issues and complications with integer programming through an example. You should all be familiar with the Banner chemicals problem. This is one we solved as a linear program in the previous lesson. Just to remind you, we're producing a high and supremium grade product. They both use the same raw materials. The capacity at the plant is set at 110 barrels. Each of the two products requires different amounts of additive A and B. You have limits on the amount of additive A and B that you have, and each grade has a different profit margin. And we asked you to find the optimal mix of high and supreme grade barrels to produce to maximize your profit. And we did that with linear programming. Piece of cake. Now we're going to put a little twist on it. We're going to say, you know what? You can only produce in lots of 10 barrels. So I'm introducing an integer constraint here. Lots of 10 barrels. So what does this look like? Well, here is what we have before for the feasible region. On the horizontal axis is the number of high-grade barrels I produce. On the vertical axis is the number of supreme grade product that I produce in barrels. And you see the grayed out area is my feasible region. It's defined by the non-negativity constraints of x sub h and x sub s, as well as the three constraints I have for additive A, additive B, and the plant capacity. We solved the solution here by mapping out the objective function, pushing that up as high a value as possible to hit the edge or a corner of the feasible region, and we found a solution of 25 barrels of the high grade, 85 barrels of the supreme grade, gives me a maximum profit, $19,000 a week. Perfect. Now what we want to do is say, you know what, I can only produce it in lots of 10. So my solution space is no longer this nice gray area where all I have to do because of linear programming is look at the corner solutions, the 5 corners. That's where the solutions are going to be. My solution space now looks like this. It's these individual dots, and these are a combination of lots of 10 of the high grade and the supreme grade. So it's no longer this continuous space defined by those constraints. It's these dots that are contained within that space. So looking at it, the number of solutions, the number of possible solutions decreased dramatically because it's just these integer values now. When in fact is what we'll see is the solution space got more difficult. There's more potential solutions to check. We'll talk about that in a second. But the question is, what's the optimal solution here if I have to stay within 10 barrel lots? So the big thing I wanted to take away from this is, well, yes, the possible solutions went down because instead of every area that was covered in that gray, it's each of these dots. The actual number of potential solutions went up because remember the beautiful property of linear programming is that it forms a convex hull and the solutions will only be in the corners. So there were really, with a linear program, only 5 potential solutions you had to check, and that was at each of the corners of that feasible region. Now I actually have all these different integer combinations to check. There's no property that I can lean upon. So what are we going to do? Well, one approach you might take is just say, you know what, find the LP solution and just round it. Find the closest acceptable integer value. This is common sense. This is a good first approach. So our solution was 25 barrels of high grade, 85 barrels of supreme grade. If I round this, I have a couple different options. First, I might say, you know what, round them both up to 30 and 90 instead of 25 and 85. And that increases my profit, but it's infeasible because it violates my plant capacity. 30 plus 90 is 120, and that's more than the capacity that I have. So what if I say, okay, I'll round the high up and round the supreme down. So I produce something that's feasible, doesn't violate a constraint, gives me 18,400. Trying the other way, where I reduce the number of high-grade barrels and increase supreme, I get a higher number, but it violates a constraint, right? I can't do that because it violates the additive B constraint. So if you look at this, then it might say, you know what, that's my best solution, 30 and 80. 30 of the high grade, 80 of the supreme grade. That gives me a profit of 18,400, which is less than my previous solution, but we expect that. But is it the best? How do I know that it's the best? And this is the problem with integer programs. Most of the times, you never know. What you really want to do in practice, a lot of times, you're looking at how close am I to optimality using the linear programming solution. They call this the optimality gap. So how close am I to what the optimal solution was with linear program? When I relaxed those integer constraints, what's my solution now? Is that close enough? Is it good enough? So we'll talk more about that later, but another approach is to see every possible solution, because I can do that now. It's each of those dots that I showed before, and I find the solution for each of them, and I'm going to pick the highest one. This is known as mass enumeration, and while it's physically possible for this problem, it's very time-consuming and almost impossible for larger realistic problems. It's like counting the number of grains of sand on a beach. But in this case, I can look at it because it's a small problem. So I'll look at the number of barrels of high grade, that's on the horizontal axis or the columns, and the rows or the vertical axis is the number of supreme. And so each cell here is a combination. It's the profit, right? I just plugged it in here, of the combination. So for example, if I produce 10 of the high grade and 20 of the supreme, or I circle 10 of the supreme grade, right? 10 of each, it would be 800 plus 2,000 or 2,800. So each cell is just a combination. It's the profit of that combination of high and supreme grade barrels. My original LP or linear program solution was producing 25 and 85. It's this dot right here, which I can't solve, right? I can't use that because I have to produce in lots of 10. And the rounding solution we found was here with 30 of the high and 80 of the supreme. However, if you look at this, the real solution is up here, where I have 10 barrels of high and 90 barrels of the supreme for a max profit of 18,800. So this points something out. Simple rounding doesn't work. Sometimes it does, oftentimes it doesn't. Mass enumeration will always show you the best, but like I said, it's very time consuming, and in realistic problems, it's not always possible to do it. It might take more time to solve that than there is in the time in the universe. Another point I want to make out is that the integer program solution, the optimal IP solution, will never be better than the LP solution. It might be equal, but it will never be better. So this gets to a property. If I add a constraint to an optimization problem, if I restrict it, and making my variables be integers instead of continuous is a restriction. If I restrict my optimization problem, the solution will never be better. You cannot improve an optimization problem by adding a constraint. It will only make it the same or worse. It'll lower the objective function. The other point I want to make is that integer programs are much, much, much harder to solve than linear programs because it doesn't rely on that nice property of corner solutions that convexity gives us. It's an important thing that you need to keep in mind when, even if you never do an integer program again in your life, you're going to use systems that are solving integer programs. Be cognizant of that because they're much harder to solve. There's a whole field involved with solving integer programming. But let's look at the formulation, because the real skill you need to develop is how to formulate these problems. Take it from the real world situation, put it into a language that you can put into a model. And so this was our initial formulation for the linear program. And so what's going to change? If I want to make sure I only solve in lots of 10, I have to convert the variables to make sure that I'm going to call it x sub hl instead of xh, and it's just 10 represents 10 barrels. I'm going to scale the coefficients and the constraints on the right-hand side. Right, so 110 barrels becomes 11 lots of 10. And I have to indicate that the new decision variables are integers. And so the formulation is going to look like this in the bottom right corner, which doesn't look that much different from the one in the top left. So the trick here is it seems so much the same. Isn't it the same when you do the formulation? When in fact, by adding this integer constraint, which is trivial from a formulation perspective, it's amazingly much more difficult to solve. So keep that in mind as you go forward solving integer programs versus linear programs. So next we're going to dive into binary integer variables, and you'll see they're used for very different purposes.